All right, Paul. Whenever ready, brother.
Okay. All right. So you starting now? Okay.
Yep.
All right. Just can everybody see my presentation first off?
Yeah, you're good.
Okay, awesome. So good evening, everybody who's attending here. My name is Paul Scott. I'm a senior here at Penn State, studying computer science, and this is a workshop on quantum computing. So I'm sure probably some of you, I'm sure you all, of course, have heard about quantum computing, but maybe aren't so familiar with how it works. It's this emerging technology that, has a lot of promise in the sense that it can, possibly could make certain computations a lot faster, could speed things up, or it can solve problems in sort of new and interesting ways. So this is really what I plan to do with this presentation is sort of give a brief overview of the basic workings of a quantum computer, what sets it apart from a traditional computer, and sort of its advantages and disadvantages to a classical computer. And then we're going to go a little bit into the math behind quantum computing because, as it turns out, it's a little bit mathematical, but nothing too horrible. Um, I'll sort of be doing a lot of step-by-step stuff, so don't worry too much about that. So the first thing I'd like to kind of discuss is what is the difference between classical computing and quantum computing. So both of them use this idea of a bit to store memory. So we have this similar idea of memory storage. But how we store this bit and how we implement it is completely different. It's completely different between each of these types of computers. So a classical approach, the most popular way, of course, is to represent a bit using transistors, because transistors can have an on and off state. Way back in the day, it used to be things like vacuum tubes, and relays could also do something similar, but the transistor was sort of the more efficient way and is the way we use today. However, the quantum approach is a little bit different in that we represent this bit using a quantum particle. So of course, just like how there's sort of multiple ways to implement a classical bit, there's multiple ways to implement a quantum bit. And so I will go into a little bit more detail about the different ways in which certain quantum particles are used to represent the 0 or 1 state. Um, and as we know, a classical bit can only have two states, either 0 or 1. However, a quantum bit can be said to be in both the 0 and 1 state simultaneously. It seems a little weird, but I'm going to go into more detail about what that really means. Um, but the truth is, we don't know when it comes to quantum particles. We don't know what state it's in until we measure it. So it's sort of almost in an undefined. I wouldn't say an undefined state, but it's in a quantum state where it has some probability of being measured 0 and some probability of being measured 1. So let's talk about the advantages of quantum computing. Why is this a field that is being researched? What's important about it? So for certain problems, quantum computing can dramatically improve runtime. So an example I'm going to go through a little towards the end of this presentation is something called Grover's algorithm, which what this algorithm does is it takes a classic search algorithm, so just basically looking through a list of items, and which runs in linear time, O of n, but the quantum search has the ability to do this in root n time. So it's a dramatic decrease in computation. It just makes it go a lot faster. Quantum computers can also solve, in general, a lot of problems they can solve quicker than classical computers, like to the point that classical computers would take years and years to solve the problem, but the quantum computer could solve it maybe in a couple minutes. So a possible example of that is breaking RSA encryption. That's very, very, very difficult for a classical computer to do, but there are algorithms that exist. There's one called the Shor's algorithm, which can be used to speed up the algorithm in order to break RSA, which is sort of one of the things that when quantum computers become a little bit more used, we'll have to kind of be prepared for, because RSA is a very commonly used form of encryption. We can also allow, though, for quantum simulations, we can use a quantum computer to actually simulate a quantum state in a quantum realm. So we can use this to model chemical reactions, which can be used for scientific and medical usages. So there are a lot of very important things that quantum computers can do well. However, they're not foolproof. So for general purpose use cases, so think about like the standard things your computers, your computer's CPU does every day, like, handles your applications, does, mathematics, simple mathematics and things like that. For just the general use case, quantum computers are actually worse than classical computers. The reason being, which we'll go into detail later, is that quantum computers are probabilistic. They have to deal with probabilities, while classical computers don't have to worry about anything like that. So quantum computers are a little less reliable, more error prone, but it's kind of built into the quantumness, I guess, of the computers, which I'll go into detail. As I already said, they may potentially be a security nightmare because it has the ability to break RSA encryption using Shor's algorithm. So I know companies like IBM are currently trying to figure out a way to make a stronger encryption that even a quantum computer would have trouble solving. And once again, quantum computers rely on probabilities, which I'll go into in a second. So let's talk about something. The basic unit of a quantum computer is called a qubit, short for quantum bit. So a qubit is a quantum particle that's in a superposition of two states, 0 and 1. So what does that mean exactly, that it's in a superposition of these two states? This means that if we were to measure this qubit, if we were to figure out what state it's in, it will have some probability of being measured in the 0 state and some probability of being in the 1 state. And while we are not measuring it, while we're just while we just leave the particle alone, it's kind of said to be in both of those states with those probabilities. And we only know which state it's in for sure until we measure it. There's a couple ways to implement qubits. One is electron spin, which we can use spin up versus spin down. We can also use the energy levels of an atom. So like the lowest level 0, highest level 1, something like that. You can also, have more than just 2 energy levels. And also photon polarization is another way we can implement a qubit, just a way to define a 0 and a 1 state with a quantum particle. That's really the idea behind all of these. So a qubit will only collapse to one of the definite states, 0 or 1, when we measure it. Until then, the qubit is said to be in a superposition of both the 0 and 1 state. So the qubit, we say, has some probability p0 of being measured in the 0 state and some probability p1 of being measured in the 1 state. So we can use these two probabilities to represent the qubit on in a mathematical basis. So a single qubit is represented using two what are called probability amplitudes. And they're not exactly equal to the probabilities themselves. So the first probability amplitude is called alpha 0, which is the probability amplitude for the 0 state. And all you need to know is that the magnitude of alpha 0 squared is equal to the probability that we measure it in the 0 state. And alpha 0 can be in the complex range. So the probability amplitudes can be complex values. And then alpha 1 does the exact same thing, except this time it's represents the probability amplitude for the 1 state. And so we can see here, if we take the magnitude squared, we get the probability of measuring it in the 1 state. And so what's important here is if we take the magnitude of alpha 0 squared and we add it to the magnitude of alpha 1 squared, it's equal to 1. And the reason being is because obviously there's only two possible states that this qubit can be in. And the probability the first state happens is this, it's p0, which is this part. And the probability it's in the other state is p1. So this is really just saying p0 plus p1. Since these are the only two possibilities, they should add up to 1. So like 100% in a sense. And then we can express this qubit using the following equation. So this is the notation. It's called bracket notation. And so this sort of vertical line followed by this arrow looking thing is just a representation of a qubit state. So what this is saying is the state of qubit alpha is equal to the probability amplitude alpha 0 on the 0 state plus the probability of alpha 1 times the 1 state. So this is just the notation that's used. And as I said, 0 corresponds to 0 state, 1 corresponds to 1. So let's continue. So we can also represent a qubit using a vector. And so, for example, instead of, for those two probability amplitudes, alpha 0 and alpha 1, we can actually write them as a two-dimensional vector where the first entry is alpha 0 and the second one is alpha 1. And it corresponds to the same qubit we were talking about on the previous slide. Now, it turns out that this bracket notation actually hides the fact that we're really dealing with vectors. So the 0 state is actually equal to the vector 1, 0. And so the 0 state corresponds to, so you can almost think about it, it's a 2-element vector, and whatever numbers inside here is the index of that vector if it's 0 indexed, such that the entry is 1. So you can see if we count this to be the 0th index, and this is the first index, the 0th index is 1 for the 0 vector, for the 0 state, and the first position is 1 for the 1 state. So therefore, we can take our equation from the last slide. It's also the same as this, so as if we just plugged in these vectors. And so then you're just multiplying a scalar by a vector. So you multiply these two together, you get alpha 0, 0. And then you multiply these two together, you get 0, alpha 1, add those two vectors together, and then we get the final vector state, alpha 0, alpha 1, which is the same as up here. So we can also just represent a qubit using vectors. Now, since all vectors must have a magnitude of 1, all qubit states, so there's a really nice thing about visualizing qubit states, and the fact that they all have a magnitude of 1, if we assume that they're real valued amplitudes, so I'm just going to assume they're real rather than complex for simplicity's sake, we can show them on a unit circle. So what do I mean by this? So let's look at this next slide. So for example, let's look at this state we're using here. So the state here, we see the probability amplitudes are 1 over root 2, 1 over root 2. So what this is saying is if I were to measure this qubit, it has a 50% chance of being measured 0 and a 50% chance of being measured 1. Because you take this number and you square it. So this squared is 1/2 and this squared is 1/2 as well. And so think about it, because we know that this number squared plus this number squared must always equal 1. If we were to draw a line from the center to the point, you'll notice that for any qubit, it's always going to just follow the unit circle, because the unit circle always has a radius of 1. And whenever we plot a qubit state such that the x value is the 0 probability amplitude and the y value is the 1 probability amplitude, it'll always have a length of 1. And so we see here's another example where we actually have some negative. So interestingly, you'll notice like these probability amplitudes can be complex, they can be positive, they can be negative. But at the end of the day, like, so when we square this number, root 3 over 2, negative root 3 over 2, because we're squaring it, it gets rid of the negative. So, we're more limited with, so maybe instead of, so there's a good reason that we're not representing these using just the probabilities, is because, probabilities are kind of restricted. They have to be positive, right? They have to be real. So this gives us a bit more flexibility as to how we can represent these states. And just something to note is that qubits on the unit circle can also just be represented using the angle on the unit circle. So cosine theta 0 for the x value and sine theta for the y value. And and also, if you can note, you can see that the 1 vector is represented by the vector alongside the y-axis, and the 0 vector is the vector on the x-axis. So we have this qubit, right? And just like any classical bit, we want to do modifications to it. We want to do some computation on it. Now, with classical computing, we have logic gates to work with bits. We have AND gates, OR gates, exclusive OR gates, NOT gates, etc. Just something that takes bits as input and gives us bits as output. Does some function. But it turns out that quantum computers also have logic gates. They have quantum logic gates instead. So we have a couple here, and actually all the ones that are listed here I'll be going into more detail about. The Polyx gate, Poly-Z gate, Hadamard gate, and C0 gate, which is controlled not gate. And there's other gates as well. So quantum logic gates, so if we think about a classical computer, can take like a bit, right? And takes a zero, it could turn a 0 to a 1, a 1 to a 0, right? Those are really the only two possible ways we can change a bit. But with a and that's sort of what gates will do, is they'll change the value of the bit to either a 0 or a 1. However, quantum logic gates will actually instead modify the probability amplitudes of a quantum bit. So it'll change the probability that we measure 0, and it will also change the probability that we measure 1. And then each quantum gate can actually be represented by a unitary matrix. And so all that really means, at least for what we'll be talking about, is it's a matrix that is its own complex inverse, I believe. But I think for gates that don't use complex numbers, they're automatically their own inverse. So I'll show you what that means in a sec. So they kind of undo themselves. If you think about it, it's like if you put two NOT gates together in a circuit, they undo themselves in a sense. So let's talk about this Polyx gate. This is one of the ones I mentioned. So the best way you can think about this quantum gate is it's similar to a NOT gate in classical computing. So if it switches the probability amplitudes of the 0 and 1 state. So if you think about that, what that means, if we start off with the 0 state and we pass it through the Polyx gate, we'll get the 1 state back. If we have the 1 state and we pass it through the Polyx gate, we'll get the 0 state. And then likewise, if we pass in a state with probability amplitude A for the 0 state and for B for the 1 state, it turns out it will flip these probability amplitudes. So now the B corresponds to the 0 state and the A corresponds to the 1 state. Now remember that we can represent any qubit like this as a vector. And so in this case, this would be vector AB. And so what we can do is we can apply that vector to this matrix over here. And this is the matrix that represents the Polyx gate. So if we look at the computation, if we have some qubit alpha 0, alpha 1, where alpha 0 is the 0 state, alpha 1 is the 1 state, we can do matrix vector multiplication, and we can apply this vector to this gate. And you can see here that eventually, and you can see the result over here where the positions are flipped. So they end up flipping the probability amplitudes. Okay, so another commonly used gate is called the Poly-Z gate. So the Poly-Z gate will negate the 1 state's probability amplitude. So for example, if you feed it the quantum particle state AB here, so you can see it, the A is unchanged here, but the B gets negated. And you can see here. And if we were to just feed this back into the Poly-Z gate, you can see that we just get what we originally had. And then so this is what the Poly-Z gate looks like. It looks almost like the identity matrix, except the lower right entry is negated, so it's -1. So here we have another gate called the Hadamard gate. Now, in simple terms, this gate's a little bit more complicated to talk about, but in simpler terms, it takes a qubit in the 0 or 1 state, and it puts the qubit in a state where the 0 and 1 states are equally likely to occur. So for example, if we feed it the 0 state, we'll get the state 1 over root 2 0 plus 1 over root 2 1. So that's the equal probability of measuring 0 or 1. And we actually have a special name for this state. We call it the plus state. This sort of equal probability of being measured for 0 or 1, and both probability amplitudes are positive. If we feed it the 1 state, it'll be almost the same, except the probability amplitude for the 1 state is negative. We call this one negative. This is the negative state. And here's what the Hadamard matrix looks like. So it's 1 over root 2 in every entry. The only exception is that this bottom right entry is -1 over root 2. So what are these gates actually doing? Because I've kind of given a brief explanation, but is there sort of another way to visualize what these gates are actually doing? So you can actually think of these um, as functions that reflect or rotate the vectors representing these quantum qubits in some fashion. So let's take a look, for example, at the Polyx gate. To think about what it does, it takes the 0 state and turns it to the 1 state. So remember, it acts like a NOT gate. It turns the 1 state and it turns it to the 0 state. So if you think about drawing a vector to the 0 state and you reflect it along the line y equals x, you get the 1 state. So it's a reflection that looks kind of like that. Now look at this. If you were to then have a vector that has equal probability of either state being measured, it would be right here. So that's where the unit circle intersects this reflection line. And so you'll notice, though, that it won't change the state. It will, when you reflect this vector and it's along the line of reflection, it's not going to do anything to it. And that makes sense. If you replace the probability amplitudes and the probability amplitudes are already both identical, it's not going to actually change the state. Then you can see, of course, let's say maybe we had one down here, which is equal probability, except the 1 probability amplitude would be negative. So when we flip the probability amplitudes, the 0 probability amplitude will now be negative, while the y1 is positive. Well, I'm sorry, the 1 probability amplitude is positive. So it rotates it, it reflects it 180 degrees over here. Similarly, the Pauli Z gate is identical, except it's rotating about the line y equals 0. So if we take the 0 vector, we'll get the 0 vector back. That makes sense because when we have the 0 vector, the probability amplitude for 1 is 0, and negating 0 is just 0 again. So it's not going to change the state. However, if we're in the 1 state, we only have a probability amplitude for the 1 state, right? And so it's would be 1 would be the probability amplitude. So then we would be negating that, turn it to -1. So now we go down here. And then finally, the Hadamard gate is a little bit different, where it rotates about the line at 22.5 degrees, which looks like this. And so you can see what happens if we feed it 0. It's going to reflect it up to here, which is 50-50, which is going to be at 45 degrees, which is going to be the 50-50% chance of measuring the qubit in either state. So 1 qubit is not particularly powerful, similar to how 1 bit in a classical computer really doesn't do all that much. It's not particularly useful. So it becomes much more useful to talk about systems of qubits. Now, adding more qubits will significantly expand how much computation we can do, but we will start to run into some issues that only exist in the quantum world and don't exist in something, or at least we don't worry about them in classical computing. But in this situation, we have to deal with quantum phenomena that can be very difficult to handle. Now, another thing we have an issue with is we should find a way to represent a system of qubits using one equation. So I already showed you how to write 1 qubit as an equation, but you really don't want to, if you have multiple qubits, you really don't want to have to write down multiple equations. There should really just be one that represents the system. And there's another reason for this, which I'll get into in a little bit, that in certain situations, we're not always going to be certain about what the qubit equation is for individual qubits, and I'll get into why that is in a little bit. So in order to combine the equations of multiple qubits, we can use something called a tensor product. So in this situation, the one I'm showing is pretty simple. We're just taking the tensor product of 2 qubits, but you can also take it of more than 2 qubits. But for a little bit, for some simpler math, I only did 2. Hold on, we got a question here. If qubits don't have definite states, how do we get concrete outputs? Are we just aiming for high probability of the output we want? Yeah, I'll get into that in a little bit, but usually at the end of any sort of quantum computation, like we want the answer that we want. So usually the answer will be, we want one of these quantum states to be definite by the end. So like when we measure it, like for example, if we look at this alpha 0, beta 0, just this whole equation down here. Yeah, so we would want, let's say if we wanted our answer to be 1, 0, the 1, 0 state, we would want it to have the highest probability of being measured. So that's part of the problem about why quantum computing isn't as reliable, because you're not always guaranteed that the answer you're going to get is 100% correct. So you'll usually have to repeat experiments more than once to kind of a quantum experiment more than once to get a definitive answer. So yeah, it's just sort of a shortcoming of quantum computing, and that's baked in though to quantum physics, that you really can't get away from the fact that quantum physics is probabilistic in nature, and so it causes some problems. But anyway, so when we're taking a tensor product of 2 qubits, you can almost think, when we're just dealing with 2 qubits, you can almost think of this as foiling. So like think about how you do that for like a quadratic equation, right? It's firsts, so firsts, then we do the outer, inner, and then the last, right? And so we can see here, so we take the first, it's going to be alpha 0 times beta 0. And then notice we also combine the states, so it's 0 and 0, so 0, 0. And then alpha 0, beta 1, and then we combine their states, 0 and 1. Alpha 1, beta 0, which we combine these states, we get 1, 0. Finally, alpha 1, beta 1, we combine the states to get 1, 1. And so this kind of makes sense, because think about what happens. Let's take the alpha 0, beta 0 for a second. And let's say that we wanted to figure out what's the probability that we get the state 0, 0. So that means both qubits are in the 0 state. So think about how you would think about this. So if we look at the qubits separately, well, it's the probability that we measure the first qubit is 0 multiplied by the probability we measure the second qubit. And what is that? Well, it would be the magnitude of alpha 0 squared plus, or no, not plus, alpha 0 squared times the magnitude of beta 0 squared. And so if you think about then this probability amplitude, alpha 0 times beta 0, if we take the magnitude of this and we square it, we end up getting the magnitude of alpha 0 squared times the magnitude of beta 0 squared. So these are, it's equivalent. So you can almost think about this as saying the probability it's in the 0 state, the first qubit's in the 0 state, times the probability it's the second qubit's in the 0 state. And you can think about all of these in the same way. So once again, we have, with 2 qubits, there are now 4 possible states we can represent, 0, 0, 0, 1, 1, 0, and 1, 1. And the 2 qubit system is represented as such, where we have phi 0, 0, phi 0, 1, phi 1, 0, and phi 1, 1, representing the probability that each of these states is measured. Once again, each of these phi's is a complex number, or can be a complex number. And when we take the magnitude squared and we add up the sum of all of those magnitude squareds of the probability amplitudes, we get 1. And that makes sense, right? So when we measure it, only one of these states is going to reveal itself. And so what's going to happen is the probability of each of these states happening added up together will be 100%, right? It will be 1. So we talked about now a system of quantum bits, of 2 quantum bits. So now I'm going to pose this equation right here. So this is an interesting equation, and notice that it only has 2 states, even though we're using 2 qubits. And I showed you in the previous slide about the states, 0, 0, 0, 1, 1, 0, 1, 1. But of course, probability amplitudes can be 0. It is possible for there to be a quantum state where a certain situation is impossible to happen. So for example, the definite 0 state and definite 1 state are both, if you measure the definite 0 state, you're going to get 0. If you measure the definite 1 state, you're always going to get 1, right? You'll never get 0. And so we don't actually need to have all four probabilities possible. We don't need all four possibilities to be possible. In this case, only two of them are. But this is a interesting equation because if you just sort of think about what this equation is saying, it's giving us a 50% chance that when we measure the system of qubits, both of the qubits are going to be 0, and also gives us a 50% chance that if we measure both of these qubits, they'll both be 1. But that's odd because it has to be one or the other. There's going to be no situation where we measure the first qubit is 1, the second 0, or a situation where the first is 0 and the second is 1. So it's odd because it would almost seem like that if you measured the first qubit first, you would then, even without measuring the second qubit, already know what state it's in because of this state equation. Because we know that if we measure the first qubit to be 0, then the second one has to be 0. And so it's kind of odd that measuring one qubit would have an effect on the other qubit, even if we don't touch it at all. Another issue with this equation is you can sort of unfoil in the same way you do a quadratic equation, but if you look at this equation, there's really no way to break this down into two separate qubits. There's no way. So if this equation represents two qubits, alpha and beta, we can't come up with equations for alpha and beta on their own. Because think about what would happen if maybe the naive thing to think would be, oh, does this mean that alpha has a 50% chance of measuring 0 and a 50% chance of measuring 1? And it kind of does in a sense, right? I mean, if you think about it, that is also true. But then we also see, okay, and then maybe beta's equation is identical. It has a 50% chance of measuring 0, 50% chance of measuring 1, which once again isn't incorrect. I mean, if you just consider the second qubit, that also just has a 50% chance. But the problem with representing those as two individual qubit equations is that you now lose this fact that if we measure 0 on the first qubit, it will force the other qubit to turn to 0. It doesn't take into account that these qubits are somehow connected to each other and they're dependent on each other. And so we call this state, and we consider the state to be entangled, which means that we can no longer talk about these two qubits individually. We have to consider them as a system, and we cannot talk about them individually. This specific state up here is called a Bell state, which is just equal probabilities of the 0, 0, and 1, 1. You can also have equal probabilities of 1, 0, and 0, 1, and it's also a Bell state. So what does it mean to be entangled? This is something I just brought up. So if two qubits are entangled, then measuring the first qubit will affect the outcome of measuring the second qubit. When measuring one qubit, the other qubit, without being connected in any physical way, will somehow be aware of the measurement we made on the first qubit in that equation I showed you on the previous slide. If we were to take these quantum particles in the real world, if these were two real entangled quantum particles, and we put them on opposite sides of our universe, theoretically, if we were to measure the one qubit and we got it to say 0, so we measured it and it's in the 0 state, and our system of qubits used the equation from the last slide, then even though the other qubit is on the other side of the universe, it will somehow be aware of the measurement and also turn to the 0 state. And what's strange about this is it's basically fast, almost feels like it's faster than the speed of light, which Einstein tells us that we can't break. And yet we've actually proven in experiments that quantum entanglement is a real phenomenon, and it happens somehow at the speed of light. Now, we don't know whether it's instantaneous or if maybe it's just faster, but we know for a fact it seems to violate this law. Now, the problem is it may not be the right way to say it because we really don't know how quantum entanglement works. So it's still a surprising thing that we can study it and we can understand how quantum entanglement functions in terms of we can understand a Bell state like on I'm sorry, like on the previous slide, but we really don't know why particles behave this way. We can tell that they behave this way through experimentation, but we don't know for sure why that's the case. So this is just a really strange phenomenon that we have to deal with in quantum computing, and this is an issue only relevant to quantum computing. Well, only it's in terms of it's not a problem that classical computers need to deal with. This is not something we have to worry about, at least in terms of making transistors that are big enough. Because one of the recent things is with transistors getting so small, you actually have a risk that if you make them too small, you actually then have to deal with quantum physics, and it gets very nasty. So the fact that we can create systems of qubits means that there probably should be a way to do work on multiple qubits. So as there are 2-bit, classical gates like an AND gate, an XOR gate, an OR gate, there are also 2-qubit gates in quantum computing. These gates must take in a system of 2 qubits. Now, the reason that you can't, what I mean by that is you can't feed in 2 separate equations for each qubit. You have to pass it, you would have to pass them in as a system. The reason being is because 2-qubit gates can accept entangled states. And so since entangled states can't be written as separate qubit equations, we want to make sure this gate can accept all possible states of 2 qubits. Now, some 2-qubit gates actually have the ability to entangle qubits together, and I'll show that in a little bit. And these gates, instead of being represented by a 2x2 unitary matrix, are now represented by a 4x4. And the reason being is because our vector for a state of 2 qubits has 4 elements, and we're applying it to a 4x4. So let's talk about this gate. This is called a controlled NOT gate, and this is a pretty important gate in quantum computing. How it works is you actually have 2-qubit inputs. The top qubit, the first qubit, is called the control bit, and the control bit handles the functionality of the second trace here, which is where the second is for the second qubit. So what this is basically if the control bit is in the definite 1 state, the second qubit will be transformed using the NOT operation. So it just, as long as the control bit is in the definite 1 state, then for the second qubit, it's identical to a NOT gate. It will just invert the state of the second qubit. However, if the control bit is 0, then the second qubit is unaffected. It doesn't get knotted. It just is completely unaffected. So the control bit basically enables or disables knotting the second qubit. And this is what this equation looks like. Now, I'm sorry, not equation. This is what the matrix looks like. Now, the reason why this is an interesting gate is because now we have to consider an interesting situation that what if the control bit is not in the definite 0 and not in the definite 1 state? What if it's in a superposition of the 2? And that's a very good question. So what happens? It would seem that that's weird because we know that the second qubit is only knotted if the first qubit's in the definite, if the qubit is in the definite 1 state, and if it's in the definite 0 state, it doesn't knot it. So then what happens if we feed it a state that's entangled or not entangled? If we feed it a qubit that's in neither of them, it's almost as if it's both 0 and 1 at the same time. It's almost as if it's really almost as if both of these it's as if it's both applying the NOT gate and not applying the NOT gate, which is very odd. So now let's look at how to apply a 2-qubit quantum gate. So we can see here's our state vector, phi 0, 0, 0, 1, 1, 0, 1, 1. When we apply the quantum gate, this is the output. So if you take a look at the input versus the output, we see that the first 2 probability amplitudes did not change. And that makes sense, right? Because in both of these situations, the first qubit is 0. And so because the first qubit is 0, which is the control bit, then the probabilities for the 0 and 1 state are not going to get flipped of the second qubit. However, in this situation, we see in both the 1, 0 state and the 1, 1 state, the control bit's 1. And so what ends up happening here is these two probability amplitudes switch. So we can see down here that phi 1, 1 goes where phi 1, 0 was, and phi 1, 0 is now where phi 1, 1 is. And if you think about why that makes sense, if we were to, let's say that phi 1, 0 is equal to alpha 1 times beta 0, where alpha 1 is the probability that the first qubit's measured 1, beta 0 is the probability amplitude that we measure the second qubit to be 0. And then we have alpha 1 here because it's the same probability of measuring the first qubit as 1, and beta 1 over here, which is the probability we measure the second qubit to be 1. So when we flip around alpha 1 beta 0 and alpha 1 beta 1, then we have alpha 1 beta 1 over here, alpha 1 beta 0. So notice that they both still have they would both still have alpha 1 because alpha 1 is talking about the probability of the first qubit, and we don't modify it. It's just the control bit. But the beta 0 and beta 1 flip as if we put it through a NOT gate. So let's talk about how we could possibly entangle two bits together. So very simply, what we could do is we could pass in an equal state of being, we can pass in a qubit that has equal probability of being measured in the 0 or 1 state as the control bit, and we can pass in the definite state 0 as the bit we're going to apply the NOT gate to. And so if you apply the math from this previous slide, you'll see that the output is actually that Bell state from earlier, where both the 0, 0 and 1, 1 state have equal probability of being measured. And so we were able to entangle these two qubits together. Now, of course, a question you might ask is if we can entangle qubits, can we also use quantum gates to unentangle qubits? And the answer is yes. Actually, if you were to just apply this gate again, so if this whole state, instead of these two individual qubit states being inputs, if this whole system of qubits is the input, you'll actually get these two states back as the output. So it's really interesting. It does undo itself. And so this is the math again. So if we feed it that equivalent state TensorFlow with the 0 state, we get this equation representing the initial system of qubits before applying it to the gate. We then take that, we apply it to our gate, and we get 1/2, 1 over root 2, 0, 0, 1 over root 2. We get the entangled state here. Okay, so I know that's a lot to take in, and I want to end this presentation off by going over a quantum algorithm. Now, this isn't this algorithm is a little bit more deeper than what I'm going to be talking about, but it's kind of how it works is a bit out of the scope of this presentation. But I'm going to give a general overview as to what this algorithm does. Oh, I apologize. It should be this one. So quantum algorithms are algorithms designed to take advantage of the power of quantum computing. Some of the more famous ones are Grover's algorithm, which is the one I'm going to be showing off. It's a search algorithm. Shor's algorithm, which is used for prime factorization, which, as I already mentioned before, can be used to break RSA encryption. And then Simon's algorithm, which is a problem designed to be solved faster on a quantum computer. So it's an algorithm that basically showcases the power of quantum computing and why it could be really faster. And so, yeah, we'll be looking at a simplified version of Grover's algorithm. Let me see. So there's another question here. So to unentangle, would you be inputting that system of 2 qubits into both the control qubit and the bottom qubit? Yeah. So I think how I showed it on that other slide, let me go back to that. So even though I wrote these as 2 separate qubits, in reality, you would be passing it in a system, the system of qubits. So you would be actually passing it in this equation right here. And so this would be your input, that would be your output. And then you would take this, output it back into the gate, and you would get this again. Okay. So let me go, okay. So Grover's algorithm, let's talk about how this works. So I mentioned before, it's a quantum search algorithm that's used to speed up unorganized searches from order n time, linear time, to root n time. So, you know, it's a very, very substantial speed up. That's equivalent to linear time versus quadratic x, like n squared, O of n squared time. They're sort of the same idea of how much of a speed up that really is. So the basic idea is we first off create an equal superposition of all states. So if we're working with however many qubits we're working with, each possible state that the system of qubits can be in have the same probability of being measured. And so what we then do is we apply one step of this algorithm that will take the element that we're looking for. So like I said, determining what element we're looking for and sort of which of the probability amplitudes to increase is up to something called the oracle in this algorithm. It's like a quantum circuit that I don't really have time to discuss, and I'm also not entirely too familiar with its inner workings. But so the idea here is the element, we want to increase the probability that when we measure this system of qubits, the state that we want to be measured, the state we're looking for, should have the highest probability of being measured. And so every time we apply this algorithm, the probability that we measure the element we want increases, while the probability we measure elements we don't want decrease. So let's kind of walk through this algorithm step by step. So the first thing is, let's just say we have 3 qubits. So we start with the state 0, 0, 0. And then what we do is we apply an H tensor product 3 gate. And all that really means is it's the same thing as applying the Hadamard gate to each qubit individually. And so now, after we take this initial state and we put it through this Hadamard, this like 3 times size Hadamard gate, we'll get all states from 0, 0, 0 to 1, 1, 1 will now be all equally likely to occur. So we get this equation at the bottom here. So now we're going to iterate. So let's say the element we're looking for is 1, 0, 0. Okay, and how do we, and the problem right now is, of course, with this equation, if we were to measure it now, we could get any of these. They're all very, equal probability, so it's not good. We're probably gonna not get 1, 0, 0. We have a 1/8 chance of that happening. So we want to increase it. So the first step is to invert the amplitude of the item we're searching for. So if we're looking for 1, 0, 0, we're going to invert its probability amplitude. And so what we'll see here is they all still have equal probability of being measured. It's just that this is now negative. And the reason we make it negative is now the second step is to find the average of all amplitudes. And so now that this probability is negative, instead of this being 8 times 1 over 2 root 2, it's now 7 times 1 over 2 root 2 minus 1 over 2 root 2. So it's equivalent to saying 6 times 1 over 2 root 2. And as a result, the answer, the result that we get is this is equal to 3 over 8 root 2. So this is the average of all of the amplitudes. So now what happens? Well, what we need to do now is invert the amplitudes about the mean. So this mean, 3 over 8 root 2, is represented by this, this green line right here. The red lines represent the probability amplitudes of all the elements other than 1, 0, 0. So 1, 0, 0's probability amplitude is represented by this blue line. So if you imagine that above here is positive and below is negative, these are all 1 over 2 root 2, and they're all positive. This is 1 over 2 root 2, but it's the negative version, which is why it's down. And here's our mean. And so what it means to invert the amplitudes about the mean is we take, you can almost think about it like this. If you were to take just the top portion of this probability amplitude and rotate it 180 degrees around the line, it just sort of goes, it will sort of intersect with the same magnitude of the amplitude over here, and they'll cancel each other out. And so you end up getting these, and this is the same for all of these, you end up getting these much smaller probability amplitudes. However, when we look at the probability amplitude of the element we're looking for, which is, which is 1, 0, 0, when we take, so now imagine we take this line, we go all the way up. So I'm talking about the line from the tip of this all the way up to the mean. And then we just take this line here and we rotate it about the mean and then add it to this existing space. We get this massive probability. So now, just after one iteration of Grover's algorithm, the probability amplitude that we're going to measure the element we want is much, much, much higher. So since we have 8 elements, we're going to need root 2 iterations, which rounds down to 2. It's 2.83, but you actually, this is an algorithm you don't want to apply too many times, because if you start to apply this algorithm too many times, it'll actually have the opposite effect, and it'll kind of undo the work you just did. So just you really should stick to root n times. So in this case, since we have 8 elements, it's root 8. So at the start, we had this state, right, with all the probabilities being equal. After the first iteration, which is this diagram here, that's after the first iteration, we see that all the probability amplitudes of all the other elements are now 1 over 4 root 2. So they're a lot smaller. However, the probability that we measure 1, 0, 0 is now 5 over 4 root 2. So it's significantly higher that we measure 1, 0, 0. And now, if we apply it one more time, it does turn all the other probability amplitudes negative, but they're still smaller in magnitude. 1 over 8 root 2, 1 over 8 root 2, 1 over 8 root 2, 1 over 8 root 2. However, the 1, 0, 0 probability amplitude now has 11 over 8 root 2, which if I plug that into my calculator really quickly, that should be a fairly large number. Yeah, so that's about a 97% chance that that element gets measured. So that's very high, right? So that's kind of what this algorithm is doing. And as I mentioned, if you repeat the algorithm too many times, you run the risk of the probability amplitude for the element you want to measure actually start to decrease. So you have to be very careful when applying this algorithm. Okay. So I want to end off this presentation by just talking about a few important resources. I think if you're still interested in learning more about quantum computing, I would highly recommend. QIS-Kit is made by IBM, and it's a really great resource for learning more about quantum computing. It goes into some of the algorithms in more detail that I talked about. I know they have one on Grover's algorithm. IBM also has something called the quantum experience, which allows you to create quantum circuits, and you can actually run them on either virtual, emulated quantum computers on classical hardware or real quantum computers that IBM offers. Although you're pretty limited as to how many experiments you can send to them. I think it's only like 5, something like that, per month, I want to say. And then finally, I understand this is just a Wikipedia article, but this goes into details about some of the quantum logic gates that I discussed today. It also has a couple others and goes into sort of more detail about the application of these gates. And you'll see that if you look up the quantum circuitry for the algorithms that I discussed, they're going to be using a lot of these similar gates. So it's usually a good idea to learn about them. And then other than that, that is it. So there's one more question. Let me see. I'm not sure if this has been asked yet, but generally, what are the limitations of quantum computing? So, like I said, quantum computers are sort of attached to probability. They're probabilistic, so they're more error prone. And you usually need to like repeat experiments to be sure that the answer you get is correct. Like if you know for a fact that, oh, our answer should have the highest probability of being measured at the end, then yeah, it's still possible it might not get measured. So you have to repeat it multiple times, but eventually if you repeat it enough, you'll start to see which one is the highest probability of being measurement from just repeating the experiments. But of course, for certain quantum algorithms, like the speed up is so significant that repeating the experiment a couple more times is not a problem. But when we're starting to, if there's really no question to me that that like quantum computers are probably not going to replace classical computers in like our daily lives. But I see that quantum computers are probably going to be something that big companies like Google, IBM, and I think even and like maybe Microsoft uses too. That can be used, especially like Google might use it for like their search to improve it. So we'll probably in the future interact with quantum computers, but because of their limitations, because they're built on probability, because like when you make a quantum computer, you actually have to make those particles like super cold in order to get reliable measurements of them, so they're not moving around. It's very cumbersome. But of course, the speed up could be very significant, but it's not guaranteed. It's not guaranteed for every single mathematical operation, only for a sort of a select few. All right.
All right, perfect. Thank you, Paul, for presenting this great workshop, and thank you to all the attendees for attending this workshop. And yeah, thank you guys.
All right. Have a great day, guys.
Yep, have a good one.